So the mean value theorem deals with slopes. That's why it's in this unit, right? It's in this unit because it deals with slopes. It deals with two slopes, okay? The first slope, that's why this is the equation or the formula for it, right? It deals with two slopes. This guy over here is a slope. How do we know this guy's a slope? Because it's a derivative, right? It's derivative, okay? This guy's a slope. Does this guy kind of look familiar? Maybe?
Yeah, that looks like the original formula.
Yeah, y2 minus y1 over x2 minus x1, right? Yep, those are the two slopes. So where do they come from? Well, picture from dot to dot. I know yours is not highlighted, but so from dot to dot. So what the mean value theorem says is, if I were to find the area, the slope from the dot to dot, from first dot to last dot, right? Find the slope. You can do that by doing rise over run, right? Or you can do that using the slope formula. Find that slope. Don't do it yet, but this is what we're going to do today. So if I was to find the slope of that green line, it connects the first dot to the last dot, right? So to do that, I need to know where it starts, right? And I need to know where it finishes, right? That's where the y2 minus y1 over x2 minus x1 would come from, right? That guy is this part right here. So this is y2 minus y1 over x2 minus x1. That's that side. Okay? So if you were to find the slope of that line that connects dot to dot, that's this side. What is the other side? Well, the other side is also a slope. But what the other side is a slope that matches. So if I was to take a journey from dot to dot, would there be a point at which the slope of the tangent line matches my green line, matches the slope? So let's see. As I go up, am I increasing or decreasing? Increasing, right? So your slope of the tangent line is going to be positive. That changes around here, right? That changes around right there, right? Because it's a relative maximum. And then after that, it starts decreasing, right? It starts decreasing, and then at the end it becomes zero again, right? So anywhere along there, was my ruler the same direction as the green?
Yeah.
It was, right? Because it started here, and then it went here, right? And then it went down here, and then it went down here. That's the slope of the tangent. That's the tangent line, right? So what x value did it have the same? A little after 2, around 2, right? We're a little after 2, because if I go here and then slip the tangent line, it would look like this, and then probably somewhere around 2, the slope of the green matches the slope of my ruler. Where is that? Around 2, right? That's this guy here, okay? So what this guy here says is, find the derivative, plug in your value. That's all it says, right? We've done that before many, many, many times. Set that equal to the slope of from dot to dot, from end, beginning to end. The reason we need the formula is because they don't give you pictures. They're not going to give you, I gave you a picture for number 1, but after that there's no pictures. So we have to do that using the formula, okay? So the mean value theorem. The mean value theorem works if it's continuous over the interval, no discontinuity, and it has to be differentiable, has to be a derivative, okay? So mean value theorem. Mean value theorem is probably the one thing, not the one thing, there's lots of things, there's lots of applications, but it's the one application that probably affects, no, I don't want to even say that, but it is, so where does mean value theorem, you see mean value theorem a lot. If you drive a car, you see the mean value theorem, or you should be aware of the mean value theorem. So the mean value theorem, what the mean value theorem says is, if you had a rate of change from beginning to end of a certain time, that means somewhere along your ride, somewhere along your journey, you had to have the same rate of change. So let's put that in a car. In a car, what kind of rate of change do we use? Miles per hour, right? So what it could say is, okay, so if you got from point A to point B and you averaged 60 miles an hour the whole way, that means you had to have gone 60 miles an hour somewhere along there at least once. How's that applicable? Well, if I'm a police officer and I time you at point A and I radio to my police officer friend and say, hey, this car here with this license plate, they just started and they got to a spot and you averaged 80 miles an hour. They don't necessarily have to catch you going 80. Mean value theorem says somewhere along the lines, you were going 80. Therefore, you broke the law. Here's your ticket. It's called the speed trap. It's called the speed trap. They trap you because they're not looking for you, right? When you crossed them the first time, you were going the speed limit. When you crossed them the last time, you were going the speed limit. But in order for you to get from point A to point B that fast, you had to have broken the law somewhere along those lines. Therefore, you get a ticket for going 80 miles an hour, whatever you did, right? Even though they didn't catch you doing it. It's called a speed trap, okay? That's why it is. So that's why when you're driving on the highway, you don't necessarily see, you know, you got to be careful. You got to be careful when you're doing it because they don't necessarily need to see you because they can use calculus to figure out you had to have gone too fast somewhere. Do I know exactly where you went 80 miles or over the speed limit, right? No, but I don't need to because you couldn't have gotten from point A to point B that fast without breaking the law. Okay? That's the big thing that you see mean value theorem. It's called speed traps. They're called speed traps because they trap you in. They don't think you're not paying attention. I crossed a guy here. I crossed the cop here. I wasn't going over the speed limit. And I crossed the cop here. I wasn't going over the speed limit. But in between, you were. So you got to be careful with that. Okay? Speed traps do exist. So you just got to be careful with those things. Okay? So that's essentially what we're doing today. Okay? That's essentially what we're doing. So example number 1. Apply the mean value theorem to the function in the indicated interval. In each case, make sure the hypothesis is true. So what do we mean by hypothesis? Make sure those two conditions are met. Make sure they're met. Okay, if they're not, we can't use the mean value theorem. Okay? This one I gave you a picture. Okay? So f of x is the graph, the red graph, and it goes from -1 to +1. All right? So they want us to find what value will it have the same slope as from -1 to +1. Okay, so let's go make a -1. So at -1, it looks like the dot is right there. And at +1, it looks like it's right here. So the first thing we got to do is find that slope. Find that slope. So we have the first dot, the first blue dot, is at -1, 0. The second blue dot is at 1, -2. So the first thing we have to do is find the slope of that line. Rise over run, y2 minus y1. So if we're going to use y2 minus y1, The first dot is negative 1, 0, so this will be x1, this is y1, this is x2, this is y2. So negative 2 minus 0 over 1 minus negative 1. So negative 2 over positive 2, which is negative 1. So this guy has a slope of negative 1. So what we just found, was this guy here. We found that side. Okay, so we're going to set that equal. So we need an equals. All right, we need equals negative 1, right? Yeah. Well, how do we find the other side? How do I find this side here? Take the derivative, right? Take the derivative of f of x. Take the derivative of f of x. Yep. So I'm going to distribute first, just because I don't want to use the product rule. So I'm going to distribute before I do the derivative. I think it'll make everything a lot easier. Oops, that's not the derivative. That's f of x. So now the derivative. 3x squared minus 2x minus 2. Set this guy equal to this guy. 3x squared minus 2x minus 2 equals negative 1. Solve for x. So I'm going to add 1 to both sides. It's a trinomial. Going to get 2 answers. All right. So let's see. A is 3, B is negative 2, C is negative 1. Negative 3 and negative 2. Need to find the two numbers that multiply to be negative 3 and add up to be negative 2.
Negative 1 and positive 2?
Negative 1. Close. Doesn't multiply to be negative 3.
Or negative 3, positive 1.
There you go.
Wait, where'd you get the negative 1 from?
C?
Here.
C is negative 1.
Here. We add 1. Right here. There's a trinomial.
Right here. The negative 1 came from the slope. The slope of the green line. Okay. All right, and then I got to divide by A. So I get x minus 1, and then this guy I got to move up, so I get 3x plus 1. So I'm going to get 2 answers. X equals 1, x equals negative 1/3. So are those both within the interval? Yes, they are, because it's brackets, so 1 counts, and negative 1/3 is inside the interval. So C equals 1, C equals negative 1/3. So all you're doing is finding 2 slopes and set it equal to each other. Find 2 slopes, set it equal to each other. So these guys here, if you ask me for help, I'm going to say 2 things. Do you have both your slopes? If you say yes, set them equal to each other. That's all it is. 2 slopes, set them equal to each other. Number 2, they don't give you a picture. So the rest of them, they're not going to give you a picture. And most of the times, they're not going to give you a picture. So how do we find slope if they don't give us a picture? For example, number 2, we have to do the same exact thing, find 2 slopes. But how do we find slope without a picture? No. How do I do this, guy? How do I do this part over here?
Because you know what x is, so we could factor out the x's and then figure out what the y's are.
Close. To find slope, I need 2 points, right? That's how I found this guy over here, because I had 2 points, -1, 0, and 1, -2. How do I find 2 points on this guy?
You just plug in x.
Plug in x, right? What are my x's?
-3 and +5.
There you go, -3 and +5. So I need 2 points. So one of them is going to be -3, 0, and the other one's going to be 5, 0. So where am I going to plug those into?
The equation f of x.
The original, yep, the original. The original, I'm not to the derivative yet. So f of -3, f of +5. So -3 plus 5, -3 minus 1. 2 over -4, which is -1/2. There's my x2 and my y2. Or sorry, my x1 and my y1. Five. So I get 5 plus 3, or sorry, no. Why do I write 3? It's supposed to be 5 plus 5, and 5 minus 1. 10 over 4, which is 5 over 2. y2 minus y1 over x2 minus x1. Okay, so I get 6 over 2, which is 3. And then I get 8 on the bottom. Okay? There's my slope, my rate of change. Now what I got to do?
Plug it into the derivative. Plug it into the equation.
No.
Find the derivative.
Find the derivative. Here's the thing. No one's brought this up yet, but I'm going to save you a lot of time. Why can I not go any further? Because you can find a derivative. It has a derivative. And then you could set it equal and you'll get an answer. But your answer will be useless. Why?
Does it not meet the requirements?
Which requirement does it not meet?
I don't know.
Yeah, there it is. It doesn't meet a requirement. Which of those conditions does it not meet?
Or continuous? Continuous.
Where is it? Where would it have an issue?
-1?
Not -1, +1, right? If I was to plug in +1 here, you'd get 0 on the bottom. Not continuous. That's a situation where you would have discontinuity. So the quicker you realize those things, you're done. Like if we had realized those things before, we wouldn't have had to do all that work. Here's the part about this. If I had never known about that, you would have gotten an answer. And guess what? It would have been one of the 4 choices on a multiple choice test, right? If it's 4 choices, one of them would be, can't use the mean value theorem. One of them would have been your answer that you would have gotten. So you just got to be careful with that. Is it continuous? That's the first question. Is there an issue with continuity? Yeah, because at 1, which is inside the interval, it's not going to be continuous. So we would say mean value theorem does not apply because f of x is not continuous at x equals 1. So if it doesn't meet the condition, you can't even okay? It's ineligible. It's ineligible for this to happen. So yeah, you would have got an answer. It's like playing a game with an ineligible player. Like a football team has a player on their team who doesn't have grades, so they have to sit out. But they let them play anyway. Well, it doesn't matter what happens if win or lose, because you're going to lose the game anyway because you have an ineligible person. It's the same thing here. You have an ineligible, it doesn't even qualify for the mean value theorem. Whether you realize that now or later, it won't have, But like I said, I've seen this happen. Students, they don't realize that, and then they do the problem like they normally would, because if you found the derivative of this guy, you'd get a derivative. And then you set it equal to here, you'd get an answer, but that answer would be useless because it doesn't apply. So always make sure you check those. Because if it's not continuous, that means there's not going to be a derivative either. Okay? All right, number 3. Number 3. So we got 2 more, and then there's just kind of previewing what we're going to be doing next week. That's number 5. Example number 5 doesn't really deal with the mean value theorem, but I put it on there because it kind of previews what we're going to do next week. Yes? Yeah, go ahead. Okay, so here we go. First question. First question we should probably ask. Is this guy ever going to be not continuous somewhere? F of x. Is there any number I can plug in for x that would make it not continuous? I don't think so. Nope. Okay, so we can continue. If it's continuous, it's differentiable. All right, so now we need 2 points, right? I need 2 points.
-6 and 3. -6 and 3.
I need an x1 and a y1. I need an x2 and a y2. So what did you say? Sorry, Seth, what were you saying?
-6 and
-6 is an x. -3 is also an x. How do I find the y's?
Plugging in numbers.
To the original. Okay, so let's plug in -6 to the original, and then -3 to the original. Okay. -6 times -6 times -6.
-198, I think.
216, actually. 216, yeah. 7 times 36. 2, carry the 2, 252. 36 times 7, carry, yep, 252. So it's going to be positive 252 because it was a positive times a positive. -24 minus 17. So -216 plus 252, 36. -24 minus 17. 12 minus 17, -5. Okay, now the same thing for -3. All right, negative 27 plus 63 minus 12 minus 17. So you're going to get 36 minus 12 minus 17. 24 minus 17 is 7. Okay, slope. We're going to use those to find slope. Okay. y2 minus y1 over x2 minus x1. 7 minus negative 5, negative 3 minus negative 6. So we get 12 over 3, which is 4. So the slope is 4. The slope from negative 6 to negative 3 is 4. Then what are we going to set that equal to? The derivative of the original, so f prime. So f prime is 3x squared plus 14x plus 4. Subtract 4 from both sides to set it equal to 0. And it becomes a binomial.
So then we just get zeros for both of them.
So let's see, yeah. So GCF is x, so you're going to have 3x plus 14 equals 0. You're going to get x equals 0, and 3x plus 14 equals 0. Okay. So I answered that question, and here are the answers. Here are the possibilities. A is 0, x equals 0, x equals negative 14 over 3. B, x equals 0. C, x equals negative 14 over 3. And D is mean value theorem does not apply. Because I've seen this. This is what they'll do. I got my answer. Which one's correct?
B.
Because.
A. I mean C. Sorry. C.
So D?
C.
Okay. C.
Yeah, C.
Because. Why 0? We got 0.
Because it's the only one within the intervals of the
There you go. There you go. You nailed it. Yep. 0's not in the interval. It's only negatives. This guy here is about negative 4 point something, so it's going to be within the interval. So the only one we want is negative 13. We already said it has no continuity issues, so this D is not going to apply, so it has to be C, yeah. Okay, be careful, because I see a lot of people, multiple choice, that's my guy. Be careful to look at that, okay? Be careful to look, because we only care within that interval. Outside the interval, don't care. Within the interval, do care. Okay? Mm-hmm.
None of them were in the interval, would it then be D?
So then, no, it wouldn't be D, because it does apply. It would be no solution or no, so it would be, that's a good question. So no value of C. So there would be no C values, or within the interval, something like that, yeah. Good question. What if both were outside the interval? You certainly wouldn't pick D because D, it does apply, it's just none of these answers fit. Okay? Yep. Okay. So number 4, I want you to do number 4 on your own. Do number 4, and then we'll do 5. We'll talk about 5. Okay? So for my slope, I got -1. Okay. And then add 1 to both sides. 3x squared minus 16x plus 5 equals 0. So you get 15 and -16, -15, -1.
Wouldn't your slope be positive?
No, y2 is 47, y1, 7. No, I got -1. Divide by a, divide by a. I get x minus 5, 3x minus 1. So then I'm going to get 2 answers. X equals 5 and x equals positive 1/3. Even though I got x, it's c. It solves, that's the value we're looking for. So those are the values. Okay? And 5 is definitely within the interval. 1/3 is not within the interval, so I'm not going to count 1/3. There's not any continuity issues because it's just a cubic. So you get one value of c, 5. Okay. All right. Okay, so for this whole thing, let me sum this up here. You're going to do 2 things. Find slope of both points. Find the slope of both points. x1, y1, y2. Find f prime. Set 1 and 2 equal to each other. Find the slope of both points, or of the line, I should say the line that's created by both points, the segment that's created by both points. Number 2, find f prime. Number 3, last step, set 1 and 2 equal to each other. Solve, you're done. It's pretty cut and dry. There's not a lot of, the big thing is the conditions. If you have something that has a fraction in it, like this guy did, you're going to have something where you have undefined. Or if you have a root, sometimes they'll throw roots in there. So they'll give you like, f of x will be a root of x plus 1 or something like that. If anything less than 1, anything less than -1 I plug in there is going to be negative. And that's imaginary, or it's going to be imaginary. So those wouldn't work. See anything else? Those are the big ones. Okay, so just look for that. All right, okay, last thing, and then we'll be done. So the nice thing about graphs, no work to be done. You don't have to calculate anything. Like the last 2 pages, all of those calculations. So next week, we're going to start looking at graphs. So on the left, 1, 2, and 3, 1, 2, and 3, Roman numeral 1, 2, and 3 are original graphs, f of x's. Those are all f of x's. A, B, and C are their derivatives. Which one goes with which? There's a couple ways to do this. There's a couple ways to do this. How do I match a derivative graph, or a graph with its derivative, or vice versa? Because that's the next thing we're going to get into. Okay, so how do you do this? Well, there's a couple different ways. First way I do is I look at the original, start with the original, look for the derivative. Look for where derivatives, start where derivatives equal 0. So if I'm looking at this guy, where would its derivative be 0? So there's no value, so it's kind of hard to tell. But so where am I looking for? So if I'm looking for derivatives equaling 0, what am I looking for? No, that would be where the value, y value, that would be where the y is 0. I'm looking for where its derivative is 0.
Where the x?
Peaks and valleys, right? Peaks and valleys, right? Minimums, relative maximums. So here, at that x value, it's going to have a derivative of 0. Which one of the threes shows that? So how do I... So its derivative is 0, right? So where should that reflect on the derivative graphs? How should that reflect? What should happen at this value here on the other graphs? Touch. So what are, these are all, so all the derivative graphs are graphs of derivatives. Those aren't y values. These aren't y values. These are derivatives, right? So on all of these guys, that's x, this is y. This is x, this is y. This is x, this is y. But on the other guys, that's not true. This is still x. But what does this represent? Derivatives. Yep, derivatives, right? Derivatives. Okay, so now let's go back and look at this guy. So when x equals this, what is its derivative? No. What is its derivative? What value, what number is it? Its derivative? 0, right? So I should go look at a graph at that x value that's 0. Which one is it? No, not A.
Is it C?
It's going to be C. Isn't this the y value, the x value that we saw before? And what is the derivative? 0. Right? So the hardest part about this is not thinking about A, B, and C as graphs. You want to say x and y. They're not x and y. They're x and y prime. Because this is a graph of all of the derivatives. It's not a graph of x and y. It's a graph of derivatives. So this one is going to reflect where the derivatives are. Well, we said the derivative is negative or is 0. So that means on the other guy, I should have something cross the x-axis there. C is the closest one. Okay. Number 2. These two guys what happens at these two guys?
Derivative is 0.
Derivative is 0, right?
So it would be B.
So it would be B, yeah. This one is B because, there we go, I get a 0 there, same spot, and a 0 there, same spot. And then we know the last guy, we know 3 goes with A because the derivative is closest to 0 here. It's not quite 0, but it's pretty close to 0. That reflects letter A there. Okay? That's the next spot we're entering. The next spot we're entering is graphs. Graphs are the easiest and hardest thing to do at the same time. Why is it easy? Because is there any work here? I didn't have to crunch any numbers. There's no work. But you got to know what you're looking for. Otherwise, you're lost. Okay? You're looking for derivatives that would show up on the other graph. Okay? The other way to do it. What happens when we find a derivative? So when we find a derivative, what happens to the function? The other way to tell. That's the one way to tell. That's the way I do it. But there's another little, it's not a cheat way, but it's a different. So what happens if I have x cubed? What is its derivative going to be?
3x squared.
So what happened to the function?
It shrunk. Or
Yeah, what part shrunk? What part went down?
the power.
The power, right? The power went down, all right? And a long time ago, I gave you guys graph sheets, graph papers. On that, it shows cubics look like that guy. That guy lives a cubic. Its derivative should be a quadratic, right? Same thing here. The derivative of a quadratic becomes linear, right? There's only one line on here, okay? 2 looks like the derivative of what? Or looks like what? Sine. It looks like sine, right? And what's derivative of sine?
Negative cosine.
Positive cosine. That's cosine right there. Okay? That's the other way to do it. That's the other way to do it. Okay? Knowing what they do. That's the other way. Sometimes that works. Sometimes if you have 2 quadratics or 2 cubics or 2 things like that, then you might have to use the other way. But if they're all different, then you can do a matching that way. Okay? That's a little preview. It's not part of mean value theorem, but I just, since this is a short lesson, I wanted to kind of preview what we were heading to next. Okay? Looking at derivative graphs. We'll do that next week.